for the third of his 3 lectures on topological data analysis, this one on multiple parameters. Take it away, Peter.
Peter, you're muted.
There we go. I think I found the unmute button. You can hear me now? Okay, sorry about that.
Yes.
All right, thank you very much for joining for the organizers again. The workshop's been great, and welcome back. So today we're going to look at multiple parameters. So up until now, we've been looking at diagrams of spaces and their homology, which is called persistent homology. And the simplest setting, which is the one we've been focusing on throughout, is the case where the diagrams are indexed by one parameter. And as I will show you, there's many settings that arise kind of naturally, mathematically, and also in applications where we really want to deal with larger diagrams of spaces which maybe have multiple parameters, and that leads to larger diagrams of vector spaces. And it turns out that we can kind of apply the same tools and approach that we've been doing, but the mathematics becomes more interesting or more challenging. And I'll outline kind of algebraic approaches to it and computational approaches to it. And then I'll end up with a new approach that uses ideas from geometric topology. All right. And before I get started, maybe the organizers will forgive me for a brief announcement. So those of you who have been willing to attend 3 of these talks, maybe you might be interested in even more. So recently, a CBMS conference was funded in topological data analysis and persistence theory, in which I will be giving 10 talks. So maybe can be thought of as an expansion of this series here. And it's not until next year, okay? So this is a really early announcement. This is very recent. There's not yet a web page, but maybe be on a lookout for that if you're interested. Or even better, maybe get some of your students and postdocs interested in this event. All right, so returning. So let's return to where we started, which is Morse theory. So we have a Morse function on a smooth manifold, and we're looking at sublevel sets of that Morse function, and we can encode all of that information in a functor. All right, so let's use that language. So a functor goes from a category to a category. In this case, the category is has a special form. It's coming from a partially ordered set. The real numbers are totally ordered, but the same construction works for any partially ordered set. So we just have elements of that poset. We have inequalities. We can think of that as a category whose objects are the elements of the poset, and there's a single map between x and y whenever x is less than or equal to y. So sublevel sets can then be encoded as a functor into topological spaces. So all of that language just says something really simple, which is that whenever A is a real number, we have the topological space, which is the sublevel set of A. And whenever A is less than or equal to B, we have the inclusion of sublevel sets. So that's a continuous one parameter family of spaces. And in computational settings, people often restrict to a finite sub diagram. So we just pick some finite number of values of the function. Usually these are chosen to be in between the critical values. So that gives us a finite one parameter diagram of spaces, which can be thought of as a functor on this poset n here, which is just the numbers between integers between 0 and n. All right, so with that with these diagrams of spaces, we apply homology. So fix a degree j and fix some choice of field k, and then we get a diagram of vector spaces, which we can represent as this composition of functors, if we're inclined to do that. And if we want to restrict to a finite subdiagram, we just start off with embedding this finite category and finite poset. All right, so that's the one parameter setting, and that's been the subject of the last two talks. But even within this setting of a Morse function on a smooth manifold, if you vary this slightly, you already see a second parameter appearing. So instead of looking at sublevel sets, we can instead look at interlevel sets. So let's fix two levels A and B, and let's look at the part of the manifold that's in between these two level sets. So now we can vary two parameters. We have a two-parameter diagram of spaces, and to formalize that, we have a functor whose indexing category consists of the intervals in R. So in particular, let's take the closed intervals in R, and so we have objects consisting of closed intervals, and we have a partial order given by inclusions of intervals. So C is less than or equal to A, is less than or equal to B, is less than or equal to D. All right, and then if we now compose that functor, that diagram of spaces, we take homology, and now we get a two-parameter persistence module. All right, and just as with the one parameter case, there's a finite version of this. Again, if we choose some finite number of levels, and then we can take intervals to be restricted to integers corresponding to that levels, that gives us, so the finite version of this gives us something called zigzag persistence. So this is developed by Gunnar Carlson and Vin de Silva in 2010. And it turns out that the zigzag persistent homology has a very nice relation to the sublevel set persistent homology using Meyerbeer-Torres sequences, and they kind of fit together in this beautiful Meyerbeer-Torres pyramid that was worked out by Carlson, de Silva, and Dmitry Morozov. So please take a look at that. All right, so here we've had multi-parameter persistence appearing kind of just very mathematically looking at a single Morse function on a manifold. Now there is also a very strong applied motivation for multi-parameter persistence. And this is something that somebody astutely asked me about in one of the question sessions, I think yesterday, is that in real data is noisy, and that can easily cause problems. And in particular, yesterday we had this very nice stability theorem, but the stability theorem used a particular metric on our point cloud, which was the Gromov-Hausdorff metric. And with respect to a different type of noise that's not Gromov-Hausdorff noise, but kind of additive noise, we'll see persistence homology ends up being brittle, and it doesn't have kind of the nice property that we'd like. So let's do something that we did in the first talk. Is we started off with a point cloud here. So we have a very idealized situation. We just take a sample of 100 points on an annulus independently. From that, we build the Vietoris-Rips complex, which we saw in my talk and also in some of the other talks. If you want to know more about its connections to geometry and topology, please look for Henry Adams's talk this afternoon. And now we take homology of this filtered simplicial complex, and this is what the persistence diagram looks like on the right. And importantly, we see the topology of the annulus appearing here. So we have homology in degree 1 has this one very persistent homology class, a point far from the diagonal, a long interval in the barcode, and that's seeing the whole, it's seeing the topology of the annulus. Fantastic. However, all right, let's add some additive noise. So let's sample 25 points on the square containing the annulus independently and add them to the previous point cloud and repeat. And now you see there's a problem, right? So here we have this big hole, and now we kind of have a smaller couple holes instead. And instead of having, if we look at the same spot in the persistence diagram where we had our point displaying the annulus, that we don't see anything, okay? So just staring at that persistence diagram, it's hard to see or convince yourself or pretend that the point cloud was coming from an annulus. All right, now, so how do we solve this? So there's a kind of a naive solution that's been applied many times since the beginnings of topological data analysis, which is to try to get rid of those points inside the annulus. And we can do that by thresholding by density to kind of get rid of all the points that are in low density regions. And there's different ways to do this. Maybe the simplest is to, for each point, measure the distance to, say, the 5th nearest neighbor. And then for points that don't have 5 close neighbors, just get rid of them. Okay, so if you do that, you end up recovering the persistence diagram on the top right from the data on the bottom left. Now, that works, but mathematically, it's very unpleasant to have to do this. In particular, because persistent homology was designed to remove the need of choosing a threshold for the scale at which we're looking at things, and choosing a particular cutoff for the density and getting rid of things below that cutoff kind of goes against the spirit of persistence. So what we'd really like to do is to look at all possible thresholds for density and assemble all of that data into one mathematical structure, and then to kind of analyze that structure. So if we do this, now we have a 2-parameter family of spaces or complexes. So one parameter would be, for example, growing balls of some radius, and the other would be including points where the density is sufficiently high. So that would give us a 2-parameter family of spaces. We take the corresponding complexes, 2-parameter family of complexes, take homology, and we get a 2-parameter persistence module. Okay, And the way to think of this mathematically is the indexing category is a partially ordered set on R to the D generally, and in the simplest case, and maybe most interesting case, R squared. And the partial order here is coordinate wise. So what do I mean by that? So AB is less than or equal to CD if A is less than or equal to C and B is less than or equal to D. Okay. Sometimes one of the parameters is more naturally going in the other direction, and you can just kind of flip the coordinates to put it in this form if you prefer, and this is maybe the standard way that people look at things. So with this partial order, if we pick a point in the plane X, then everything that's greater than or equal to that point lives in this quadrant here. So Y here, we'd have X less than or equal to Y. So that'll be true for all the points in this quadrant. All right. And maybe now is a good time for me to take a breath and make a disclaimer or encouragement that I've been making in the other talks, is to please ask questions. Use the chat feature or even use the unmute feature to interrupt me and ask questions. So, the organizers will let me know if there's a question in the chat. I'll take that to mean there's none so far yet. All right, so with this diagram of spaces, we take homology, we get a 2-parameter persistence module. Okay, so understanding these is a really, really important mathematically. Smoothing data is ubiquitous, and if we could say something, kind of give a global view of something about smoothing data, that would be incredibly useful to data analysts. All right. So let's try to study these multi-parameter persistence modules, and I'm going to do algebra here, which, I mean, persistence modules are an algebraic object, and there's equivalent ways of looking at it through the prism of different parts of algebra. So the one I've discussed already is we can think of it as a functor. So we can maybe try to do a bit of category theory to understand these things. And from the continuous point of view, we have a functor from R to the D into vector spaces. The discrete point of view is that we restrict to the integer lattice, and we have a functor on that into vector spaces. And the further restriction is we take a finite sublattice. So that's kind of the computational setting of multi-parameter persistence modules. Now, that's good for applications, and it's also good for people from a particular part of mathematics, which is people who study quivers, because a finite lattice is a special case of a quiver, or a quiver with relations in particular, because we want the squares to commute. And so we can apply some of the great results of quiver representation theory to multi-parameter persistence modules. And in particular, there is a famous and wonderful theorem of Gabrielle from 1972, which tells us kind of everything we want to know for the one-dimensional case. It says that every multi-parameter persistence module, meaning every quiver representation of a one-dimensional finite quiver, can be written as a direct sum of indecomposables, and it tells you exactly what the, Gabrielle tells us exactly what the indecomposables are, and they are exactly interval modules, okay? So this is something that we knew, and now we realize that we just rediscovered the theorem of Gabrielle's. Now, unfortunately, So that's the good news from representation theory. There's also bad news from representation theory, which is that representations of quivers quickly get very, very difficult. And in particular, once we get to d equals 2, classifying the indecomposables, which we might naively want to do, is hopeless. And this is a theorem. So to state this as a theorem requires a bit more care. But the essential idea is that if you take one of these quivers like this one at the right here, if you were able to write down all of the indecomposable modules of this quiver, then you could write down all of the indecomposable modules of any quiver. All right, so there's a theorem that tells us that. And so essentially this kind of classification of indecomposables approach is not going to go anywhere if we want to get all of them. Of course, we're only interested in applications, so maybe we don't want all of them. We only want the ones that appear in applications. So I think that might give us hope for maybe pursuing this direction from a kind of an applied point of view. All right. There's another way of thinking of persistence modules as here they actually are modules in the algebraic sense. They are graded modules over the graded polynomial ring. All right. So how do we interpret, say, representations of vector spaces on the integer lattice as modules over the polynomial ring? So the location of your vector space on the integer lattice gives you a grading by z to the d. And then there's an action I claim of the polynomial ring on this. So well, the ground field just acts by scalar multiplication. And then I need to tell you how each of the variables acts. And the action of x1 in this case is just given by these maps. The horizontal maps can be interpreted as the action of x1. And similarly, the action of x2 can be interpreted as the vertical maps. And notice that these are graded maps. They increase the grading by 1 in that direction. So each of the variables has a grading of 1, or specifically kind of 1, 0, 0 for the first one, and so on. All right. So again, we have good news for d equals 1. Polynomial ring in one variable is a PID. We have a structure theorem for modules over a PID. And in fact, this was the original proof that we could decompose discrete one-parameter persistence modules into barcodes by Carlson and Zomerodian. They used this result. Now, the good or the bad news is that for d equals 2, of course, things get much more complicated, and there's a whole field of commutative algebra dedicated to studying this situation. And there's lots of interesting things, and things get difficult. And in fact, for persistence, we kind of want even more than what's usually studied in commutative algebra, because we're really interested in the continuous case. And the continuous case can be dealt with algebraically by letting us take polynomials with real exponents. Instead of just taking polynomials with integer or non-negative integer coefficients, we can take non-negative real coefficients. And so this is a theory that's being developed, and in particular, Ezra Miller has done a lot of really interesting work on this. And the place to look is, there's, I think, 4 archive preprints from 2020 is the latest version of his work. So if you're interested in that, please take a look at that. One other kind of algebraic approach to multiparameter persistence modules uses sheath theory, we can view them as sheaves over R to the D with the Alexandrov topology. So that is the right way of kind of encoding the partial order structure of R to the D into a topology. And then we can look at sheaves over R to the D with that topology. So this has been a lot of work's been done by Justin Curry, also by McPherson and Patel, and more recently by Kashiwara and Shapira. All right, so if you're interested in sheath theory, please take a look at that. All right. Now, so that's all I have to say about the algebraic point of view. I want to say a little bit about the computational point of view. Because of the kind of mathematical difficulties of doing multi-parameter persistence, all of the main computational approaches that I'm aware of depend on one parameter results. So they kind of reduce the multi-parameter situation to the single parameter situation. And we do that by restricting our multi-parameter persistence modules to certain one parameter affine lines sitting inside R to the D. Oh, and then we look at all of them and we assemble that information into a summary of what's going on. So unlike so this of course is not going to give us complete invariance, but it does seem to give us computational summaries that are useful in practice. So perhaps the main work in this direction is Rivet, developed by Mike Lesnick and Matthew Wright. It's both a computational and visualization tool for multi-parameter persistence. There's a few ways of extending distances and kernels from one parameter persistent homology to the multi-parameter setting. The bottleneck distance can be extended to the matching distance. The Wasserstein distance can be extended to the sliced Wasserstein distance, and persistence landscapes can be extended to multi-parameter persistence landscapes. All right. So that's all I have to say about, so that's the state of the art, or that's a slice, very brief introduction of what's been done for multi-parameter persistence. And for the remainder of the talk, I want to introduce a new approach. And I think it's one that I'm very excited with, and I hope you will be interested in it as well, because it's particularly aligned with this workshop because it uses ideas from geometric topology. And so this is joint work with Mike Catanzaro, and our idea was to go back to Morse theory. Let's go back to the beginning. And so persistent homology, we were in the very beginning of the first talk, we thought of as a descendant of Morse theory. And we're now interested in kind of a parametrized persistent homology. And parametrized versions of Morse theory have been developed. And so let's take a look at what's been done and see if that can be useful for doing multi-parameter persistent homology. So first, let me say something about Morse theory that I didn't talk about in the first talk, but is an important part of the subject, which is that Morse functions are generic in a certain precise sense. So if we look at smooth functions on a smooth manifold, an arbitrary such function can be approximated by a Morse function. So first of all, let me say more precisely what I mean by Morse function. So this is a smooth function, all of whose singularities, so places where the gradient vanishes, are non-degenerate. meaning that the Hessian, the matrix of second order partial derivatives, has full rank. And there's an additional condition that we can add here, which is that the critical values are distinct. So no pair of distinct critical points shares a critical value. All right, now if we look at the class of all such functions, it turns out that they are an open dense subset of smooth functions from M to R with a particular topology with the Whitney topology. Okay, so if we take an arbitrary function, there is a sequence of Morse functions converging to it, or we take any neighborhood in this topology of that smooth function, there's a Morse function in that neighborhood. And if we take any Morse function, that function has an open neighborhood consisting of only Morse functions. All right, so that's very classical and very well-known theory. And also classical theory, but maybe less well-known, was developed by Jean Cerf. And so he was a student of Henri Cartan, and so he extended this result of Morse theory to one-parameter families of smooth functions. Now, the initial dream you might have is that you can do the same thing and approximate a one-parameter family of smooth functions by a one-parameter family of Morse functions. Stated equivalently, or stated a little more sharply, what you can do is take any Morse functions and now consider a one-parameter family of functions that interpolates between them. So we have a path of smooth functions between two Morse functions. Can we take an open neighborhood of that path? Is there a path in that neighborhood consisting of only Morse functions? The answer is no, but we get very close to that. So this is a result of Cerf's, that we can find a one-parameter family of functions that's Morse almost everywhere. It's Morse at all but finitely many points along that curve. And we can say exactly what goes wrong at the remaining finitely many cases. And kind of two things can happen, one of which is very minor, which is that we can have two critical values that are equal. And the other one is more interesting, is that we have kind of a new phenomena appearing. And this is kind of a cubic phenomenon, not a quadratic one, which is that we have a birth-death singularity. So what is that? So the birth-death singularity is on the right here. And the more generic situation is on the left, which is that as we move along, so t here is our parameter going from left to right. So for any fixed t, we have a Morse function here, we have a parabola, we have a critical point, and kind of as we move along, the critical points are on the pink part here. We have, putting them all together, we have what's called a fold singularity. Now, in some cases, fold singularities can cross. So this is kind of the first case. So we got finitely many places fold singularities might cross in their values. So that's okay, and that's not so interesting. What's more interesting is these birth-death singularities. And here, if we are moving from the left to the right, we have here two critical points that come together and annihilate. So that's called a death. And if we move in the opposite direction, we have a birth. Okay, so this point here is the birth-death singularity. And this is kind of these are the only added complications that we get from a Morse function to a one-parameter, going from smooth functions to one-parameter families of smooth functions. All right. Okay, so let's use these results for persistence modules. And so again, this is joint work with Mike Catanzaro. And so let's start off with a one-parameter family of functions. And it's convenient to encode them in the following way. So usually a one-parameter family of functions is written as a function on x cross I or I cross x into the real numbers. It'll be convenient for us to keep track of that parameter value. So we'll actually map into I cross R. So we're fibered over I, if you like that language. So I should say that I here is the unit interval, closed unit interval. All right, and now we have this diagram of spaces indexed by intervals of I cross R. All right, so for any closed interval in the unit interval, so any closed interval AB, and any real number C, we look at the inverse image of their product, which is a semi-infinite strip. So what does that look like? So if we have here, that's terrible. Let's try that again. So if we have here between 0 and 1, so if we have AB, and then we have a height C, our semi-infinite strip will look like this. And we'll look at inverse images of these semi-infinite strips in the graph of F. All right, and that gives us a diagram of spaces that has 3 parameters. And taking homology, we get a persistence module that has 3 parameters. Okay, so that's the setup. And let's look at some examples. And before we do that, actually, I need one other convenient tool that's called the Cerf diagram. And this is just a nice visualization of the singularities of that one parameter family of functions. So this is just a graph of the singularities together with the parameter value of the function. Okay. All right. So we have one parameter families of functions on manifolds, and the simplest case is the dimension 0 case. All right. Smooth functions on closed 0-dimensional manifolds are not so interesting. They're just constant numbers. But if we take a one parameter family of them, then now we get functions from R to R, which are a little bit interesting. We teach students calculus. So what's kind of a simple case is just looking at a quadratic function. Here we have an example that sits on the unit interval and ends up lying in the unit interval. Let's look at the corresponding diagram of spaces and diagram of vector spaces. To make my life a little bit easier and to allow me to make exact computations, I'm going to replace it with a piecewise linear function. All right, so it's not smooth anymore, but that's okay. So let's look at this piecewise linear function on the unit interval that goes up and down as a max at 1/2. And so we have this 3-parameter diagram of spaces. So it's a little bit hard to see all of that at once. So let me pick a finite subdiagram here. So we have a, this here is a subdiagram of F. All right, so I've picked 4 combinations of A, B, and C. And let's look at let's look at this one here. All right, so let me remind you that F, actually I'll just write down the formula again. F of A, B, C is equal to F inverse of AB cross minus infinity to C. All right, so what do we need to do? In this diagram on the left here, this graph, we look at semi-infinite strips. So in particular, we can look at this semi-infinite strip here corresponding to A equals 0, B equals 1/2, C equals 1. So what does that look like? So C is 1/2, A and B are 0 and 1/2. So we have this semi-infinite strip here. And we look at its inverse image, which is just its intersection with this graph. So the space that we have at the bottom left here is exactly this subset of that wedge of those 2 line segments. All right, so it's contractible space. Okay, so we go to this F here, and now we take homology in degree 0. Things are one-dimensional, so that's kind of the only interesting homology. And since it's contractible, H0 is just going to be K here. All right, now we can do the same thing kind of on the right-hand side, which is over here. That's looking at the inverse image of this semi-infinite strip here. And again, we get the same answer. And now we can look at the union of those 2 semi-infinite strips. That gives us the union of these 2 line segments. So H0 is now and now we have a 2-dimensional vector space. The inclusion maps can be given by the inclusion of the 2 kind of one-dimensional orthogonal pieces in this 2-dimensional vector space. And then when we go up to the height C equals 1, then we get all of that line segment, which again is contractible. So we have the diagonal map on the 2-dimensional vector space to the 1-dimensional vector space. All right, so all of this is very, very elementary. But what we end up with is something that's slightly interesting is this, what we have on the right here is a representation of a particular quiver called D2. And it's not hard to check that it's indecomposable. So this is something that's different that we didn't see in the 1-parameter case. It's a persistence module that has dimension greater than 1, but is still indecomposable. Okay, and by kind of building up this example just a little bit, by kind of going up and down a bunch of times, that you get, we prove that you can get indecomposable persistence modules with arbitrary high dimension. All right. Now, let's try to visualize not just those 4 spots, but all of the spots in those 3 parameters. So remember the parameterization. So actually the only homology here is H0. So, and H0 of F was on intervals in I cross R, and intervals on I is, or were of the form like this. And you may recognize that actually as the 2 simplex, the triangle. So our multiparameter persistence module is indexed by a triangular prism, so a triangular cylinder, triangle across R. And in this case, C is below 0, we have the 0 module. C above 1, we just have the 1-dimensional module. And kind of in between is where things are interesting. And we have the interesting parts are coming from the kind of the 2 legs of that triangle. So one of them we see here, and the other one is here. As we go up higher, there's kind of a larger width of intervals that see that leg. So we have it kind of growing wider and wider. And if our interval is sufficiently wide, then it sees both of them. And in that case, it's 2-dimensional. All right, so this is kind of a graph of the Betti number, the 0th Betti number for this persistence module. And the maps are kind of internal to that. And that map that I had on the right is embedded here by these arrows. So we see here this irreducible representation of D2 sitting inside that persistence module. All right, I have 2 more examples. I mean, the 0-dimensional manifolds are not so interesting. So let's go up to 1 dimension. So we have functions on the 1-parameter functions on the circle. And the simplest case is a constant height function on the circle, or the height function on the cylinder. And let's graph the Cerf diagram for that. So this is the Cerf diagram. So there's only kind of 2 singularities from the local, for the minimum and the maximum of the height function, and those are constant everywhere. And now if we take these semi-infinite strips and their inverse images, there's really only 3 cases. So the values of A and B make no difference. It just matters on the height C. If C is below -1, we have the empty space. If C is above, between -1 and 1, then we have kind of a ramp where you could skateboard. So we have kind of a thickened arc of the circle. And once we go above 1, then we have a cylinder. Okay, so in terms of we can draw a picture for this multi-parameter persistence module. Here the blue is H0, and red here is H1. So both of these are triangular prisms, or kind of semi-infinite triangular pyramids, one of which is born at C equals -1, and the other, which is H0, and the H1 is born at C equals 1. All right, so that's nice, but kind of simple. So I'm going to end my talk with one example that's, I think, non-trivial and interesting. And this is something we call the wrinkled cylinder. And it takes the cylinder and adds in a wrinkle. So a wrinkle in the sense of Eli Ashberg and Mishachev. All right, so Eli Ashberg and Mishachev used these wrinkles to study maps without higher singularities. So understanding a Goose's theorem. And so in the late 90s, they worked this out. They have a very nice GSM book, Introduction to the H Principle, that goes into detail on their work. So that's in 2002. So take a look at that. And so the idea is to take a wrinkle, so take a cylinder and introduce a wrinkle. So kind of just like your shirt, we add a wrinkle, and it's a little hard to see in this picture here. So I'm going to share an animation of this that Mike constructed. So let's see if I can do this. I'm going to switch sharing here. All right, so hopefully you can see the same picture I had on my tablet just a second ago. And so we have this wrinkled cylinder, and kind of faintly here you can see what the one-dimensional slices look like. And as we move, so this is the one parameter family functions on the circle, and right here we hit a birth-death singularity, and it's kind of faint, but you could see that we get two additional singularities, and we have a wrinkle in the circular slices. And then as we go further and further, they get bigger, and then they get smaller, and then eventually we hit the other birth-death points, and then now we just only have the two singularities on the circle. And we can see all of that a little bit better. Let me rotate the cylinder. Try to find a good view of it here. Let's start over again. So this is kind of a side view. So you see that wrinkle inside the cylinder. All right. Okay, so I think that helps us hopefully see it better than we did in the static image. All right, so the Cerf diagram of the wrinkled cylinder is on the right here. Again, kind of on the left and the right ends, we just have the two singularities. And then in the middle, we have four. And then we have these interesting two birth-death points. Okay, and now for our diagram of spaces, we look at inverse images of these semi-infinite strips. And in many cases, it's just the same as what we had for the cylinder. The places where it's different is where our semi-infinite strip intersects the wrinkle. All right, and here I have two cases where the intersection kind of sees the fold that's coming down from the bottom half of the wrinkle. And in this case, our inverse image has two contractible components. Now, what's even more interesting is if we look at this semi-infinite strip that kind of intersects the top of the wrinkle but doesn't contain any of it. And you see here what the inverse image looks like on the left. It's seeing that wrinkle, the fold of the wrinkle, but sliced. So we see something that's homotopic to the circle. So we have an extra H1 that we didn't have when we looked at the circle. Okay, so now with a bit of work, or a lot of work, one can visualize this. So this is a picture of all of the H0 and H1 of our wrinkled cylinder. So let me guide you to this visualization. So there's three pieces to it. On the left here, we have the same H0 that we saw from the cylinder. So it's this triangular pyramid that's born at the minimum value and then extends all the way to the right. And then at the height of the cylinder, we have a component of H1 that's born and lives forever. Okay. And now in the middle, we have something that's interesting. So this is in the wrinkle. So this is the part coming from the wrinkle. And there is a H0 part, which is in blue. That's coming from the connected component of that fold. And then the most interesting part maybe is the H1 that's coming from the top part of the wrinkle. Okay. And so this gives us a decomposition of our multiparameter persistence module into 4 indecomposable modules. And in this case, they are all one-dimensional. All right. So that's all I have to show. So let me kind of just end my talk with a plea or a request that I think there's lots of, that trying to do this involves some interesting ideas from geometric topology. And since there's lots of experts in the audience, those of us in the topological data analysis community would be really excited if you have something interesting to say using all the things you know about geometric topology about these types of problems. So please let me know if you have more to add to this story. And with that, I will end my talk. Thank you very much.
Okay, let's all thank Peter, not just for this talk, but for the full 3 wonderful talks he's given us.
Yeah.
So who has any questions?
Greg, I'm sure you're going to have some questions for Peter, but I just wanted to jump in here. If people who have been looking at the website see a long list of organizers for this workshop, but I want to point out that Molly Moran and Greg Friedman did almost all of the work for getting this thing together, and I think we should give them a round of applause for all the work they've done.
I think we should thank all the organizers. So yeah, please join me in thanking all the organizers. So thank you.
Thank you. So yeah, questions for Peter.
Scott, go ahead.
Hi, thanks for a really excellent series of talks. Thinking about the sort of the way I know of that's like Cerf theory or parameterized Morse functions have been used in, say, 3-manifold theory, is that one use has been to try and pinpoint Morse functions that give particular topological information about, say, the 3-manifold or knots or links or whatever. And when I've thought about this in the context of topological data analysis, I've wondered if there are, if you like, as you think about like expanding the little neighborhoods around the points as you form your persistence diagrams. I mean, you can imagine expanding those balls at different rates based on different points, and maybe there's like some optimal choice for, you know, how you're like, should all the data points be treated the same or not? And I've been curious as to whether or not that's been something people in your community have pondered or thought about, kind of what's the optimal Morse function?
Yeah, so that's a great question. So I definitely think people of a computational bent have done and thought about these kinds of things. Maybe a pointer term is that there's a weighted alpha complex. So these check complexes in in low dimensions are kind of best replaced with a Delaunay complex or an alpha complex, which is kind of getting rid of some of the extra intersections that aren't needed. And there's weighted versions of these that have been used and studied. I mean, I think more generally, people like sampling things computationally definitely use the idea of kind of sampling more heavily in places where there's interesting features. So this is used a lot by people in computational geometry, for example, and there's been some spillover into computational topology with those ideas. As far as I know, no one has thought of that in terms of Morse functions, and even phrased the problem as like finding the right Morse function. And it might be that that is a profitable thing to do. Yeah. I also think that it might be also profitable to think of all of those choices as like a family of Morse functions, and then as you said, is like kind of finding the right spots where maybe there's some topological changes in this configuration space. Yeah, I mean, just generally, can we like look at configuration spaces of choices of parameters that are used in applied problems and study those configuration spaces topologically and say something global? I think all of these are hard things to do, but they seem to fall kind of within the framework of things that topologists have been studying for a long time. And we've had some big dramatic successes in understanding configuration spaces. And if we could do that for one of these applied problems, I think it would really have a big impact outside of mathematics.
So I've got a very broad question for Peter. You know, just within the, I guess almost all within the last decade or so, applied topology broadly and persistent homology in particular have become sort of huge areas. And so do you have specific recommendations for people who want to get into that area, or students who want to get into that area? Where's a good place to start in terms of things to read or ways to learn this kind of thing?
Yes, okay, thank you for asking that. I've been asked this often enough that I should be able to answer your question. But first of all, let me maybe make a contention with your comment. Topological data analysis is still a tiny area, I think. I mean, for one thing, mathematics is a small area. I mean, once you start working with people in other areas like biology, there's way more biologists than there are mathematicians. People doing data science, there's kind of hordes and hordes of people doing machine learning. People doing things in those subjects with a mathematical background are really a small minority. Topological data analysis is a small group in those subjects. Topological data analysis is small in mathematics. I mean, it's still a kind of a small part of topology. So I say that as a good thing. If you're interested in getting into the area, it's still very new. There's not many of us in the area. There's not a lot of papers. The theory is just being developed. There's still lots to be done. There are still basic theorems waiting to be proved. There are still basic ways of looking at things that are waiting to be defined. And so that's one of the things I find exciting about the area. The other thing about the area that I find particularly exciting is that it has lots of great connections, both within mathematics and outside of mathematics. So I've tried to highlight a few of those. but there are many others that I have not touched upon, connections with probability analysis, geometry. There's many interesting connections in those directions that I didn't even talk about. So if you have kind of background in a particular area of math, you can maybe just take a peek into this world of applied topology and see if there's a part of it that connects to things that you know about. And if it does, then there's maybe likely the way that you can kind of build a bridge to expand the subject, and maybe also to kind of connect parts of your math to things that have connections outside of math. And that's something that's also exciting about this area, is that it's very easy to find places where you can do computations using some of these tools that are topological and connected to things outside of math, which for one thing means I can now kind of talk to people who I don't know and ask me what I'm working on. And instead of having to say something about trying to explain homotopy theory, I can instead talk about an applied project that I'm involved with, and then maybe that might be easier to understand. And in particular, you can give undergrads things to work on that that might be easier to connect, for them to connect to, but then also kind of have connections to some interesting mathematics. All right, so I went on a kind of a long detour, and I didn't actually answer your main question, which is what concretely should you be doing to get into the subject? And well, first, the bad news is that since the subject is new, there aren't a sequence of textbooks written for all the people who might want to be entering the subject. But there are a few now. So in particular, there is a great textbook by Steve Udo, and you can find a link on my webpage. It's in the AMS graduate text GSM series on persistence theory. So it's aimed at graduate students. So that's a good place to get into the book in a fairly way to get into the subject in a fairly comprehensive way. For undergrads, it's maybe a little too technical. There is not yet a great standard undergraduate level textbook. There are a few books or monographs that are written towards a computer science audience. Again, I have links on my webpage. If you're, I mean, one thing is you can just pick up some papers. I think the papers in the subject, because the people in the subject are kind of have a broad background, many of the papers try to be kind of more accessible than your standard math journal articles. So just picking up some papers might give you stuff that you can read. And now if your interest is more computational, then I think the right thing to do is to just pick some software and start computing some stuff. There's a number of packages. Again, you can search for them. I have some links on my webpage. I've developed some stuff in R, which is a statistical language that's kind of lightweight and easy to use. I have some stuff on my webpage. I have some stuff I used in a course last fall that I would like to put on my webpage soon. I have some older versions of it there. You can maybe email me and I'll do something. What I really should do is have a GitHub page that has this. This is what my students and postdocs do, but I haven't quite caught up to them on doing that. There's also a bunch of nice survey papers, and actually that's probably the best place to get started. Again, I have a link to a bunch of these on my webpage, so take a look at those survey papers. And they vary in kind of the level of mathematical detail. So I think most people should find something in those survey papers. And there are actually now great YouTube videos introducing persistent homology. So look for those. I have links to a few of them on my webpage. Yeah. And of course, now we have lots of great talks. So there's the Applied Algebraic Topology Research Network, which has been hosting talks in topological data analysis for quite a few years now. They're very active. Sign up and watch their current talks. And they have a great catalog of talks that are all on YouTube. So that's another good way to maybe get some exposure to the subject.
Thanks, Peter. And that reminds me, a number of people have been asking when these videos will be posted. And the answer is probably sometime in about a week or so, as soon as Molly and I have a chance to get them up on our YouTube site.
I think there's also a good chance Jose wanted to say a little bit more about this workshop next summer. So I'll let you say that and then I'll get to Tish's question.
Okay, thank you so much, Molly, for giving me the opportunity to say something about this conference. As Peter said at the beginning of his talk, is a CVMS conference that is going to be held at the Valdosta State University in Georgia, very close to the border with Florida. The idea is that Peter is going to give 10 lectures, and then so it's going to become an extension of this series of lectures. And the people will have plenty of opportunity of discussing with others about the topics of the conference and about other type of math that is being done related to topological data analysis and persistence theory. So then I have planned to have a website set up before the talk today, but there were some issues with the server at Valdosta State, but then a site should be up sometime next week. And then I'm going to send an email to the organizers of the conference so that email is forwarded to the people that participate in these talks. Thank you so much.
Thank you. Atish, if you want to ask your question.
Yeah, I had a question about, so in usual one parameter persistence, as you told us earlier, last 2 days, the end visualization of the pipeline is these persistence barcodes and the eventually persistence diagrams. In this 2-parameter persistence, do we have the same visualization through the affine lines, or so you go through the affine line and get the barcodes and diagrams, or there is something combined?
Yes, so great question. So the answer is yes. So if we restrict to affine lines in R2 is the case where people are working, then for each of those one-dimensional slices, we have a persistence diagram. And so the software package Rivet will visualize these. And in fact, it will, after it's done building some interesting internal mathematical representation, it will dynamically plot these persistence diagrams as you sweep through the plane with these affine lines.
So, so in the case of the salt and pepper noises that Thomas talked about yesterday, what would you see then in that case?
That's a good question. So I haven't done this for that example. So what would happen? So initially, so if we have all of, so I guess we want to have increasing spaces as we go from left to right. So initially we would have no points. The threshold of density would be too high to consider any of the points that we have. So we would just have the empty diagram. And then we would, at the opposite extreme, we would have all of the points, and then we would have the persistence diagram for the points on the annulus together with the salt and pepper noise. And then I guess in the middle, maybe we would have thresholded out those kind of troublesome points in the middle, and then we would have kind of a cleaned up persistence diagram, which would kind of look nice. And then as we move from left to right, what we would probably, well, things would grow, and I guess what's maybe most interesting is on the right half of that diagram. So in the middle, we would have kind of the salt, sorry, the far right, we would have the salt and pepper noise. On the middle, we have the cleaned one. And then if we kind of move from right to left, what we would see is that that one point that's furthest from the diagonal in H1 would grow or move away from the diagonal. And we would see kind of that persistent homology class of the hole in the annulus kind of growing as we go to that. So it would keep growing and growing until at some point it would disappear because we wouldn't have enough points on our annulus to kind of have a sample that goes all the way around. Okay, so that's what I think would happen.
Thank you. Yeah.
Who else has questions? Maybe everybody's worn out after 3 days of talks. Actually, that reminds me also a brief reminder that the schedule this afternoon is slightly different. We have fewer contributed talks in the sessions this afternoon. So instead of doing 3 talks a break and then 2 talks, it's just going to be 4 talks straight through, but starting at the same times.
Well, if nobody else, then may I ask another question to Peter?
Sure.
So once you showed this Barthes singularity surface, so was that for the two parameter? I was a little confused. Was it from a 2 parameter thing, or was it from the Cerf diagram? The surface you showed for birth-death singularity beside the fold singularity.
Yeah. Well, let's take a look at that again, because it's probably. I mean, I've spent a lot of time staring at these, and if I haven't done it for a while, I kind of still need to remind myself how everything works. So I'm sure that it was maybe a lot to take in kind of briefly. So. All right, so we have this wrinkled cylinder, and I'm thinking of this as a 1-parameter family of functions on the circle. So on both ends, we just have the usual height function on the circle. And then in the middle, we have a height function. We have the graph looks like a circle with this extra little wrinkle in it. So we have 4 critical points instead of 2. Okay, so those are kind of the interesting slices. Kind of going through here, it looks something like this. Okay, so that would be kind of cutting through the wrinkle here. So we have the 4 critical points are these 4 here. Okay, so this is degree 0, 0, 1, and 1. Okay, and now we spent a long time thinking about what the right way was to turn this mathematical structure into a persistence module. And what we came up with is not the only way to do it, but we think it's kind of the right initial way to do it. And it ends up having 3 parameters. So we look at, so what we're really looking at here is we encode this as a fibered map. So it's I cross, sorry, in this case, S1. So I cross R. So we have a map from the cylinder onto the plane. And we look at inverse images of parts of the plane. So if you like doing sheath theory, then you might just look at an arbitrary open subset of the plane and look at the inverse image of that. That'll give you a subspace of the cylinder and take the homology of that. One can do this, and that's kind of the ultimate persistence module, because it kind of has everything, but it's maybe overkill, and it's certainly gonna be hard to visualize. So we chose to take inverse images of particular closed subsets, and we chose these semi-infinite strips. Now, they're kind of a combination of the two versions earlier, which is sublevel sets and interlevel sets. So there's sublevels sets in the value C, and then they are interlevel sets in the parameter value. And it certainly gives you something interesting. And it also, I think, should be thought of as an intermediate step to interlevel cross interlevel, which is maybe the more natural thing to do, and look at inverse images of rectangles. But my feeling is that using kind of Meyer-Vietoris arguments, you maybe will get not much more extra information than what we have from this point of view. And also it takes you up to 4 dimensions, which then really gets to be a pain to try to visualize. So the dimensions here are, so it's A, B, and the height is C. So for each combination of those 3 numbers, we now have a vector space and a dimension. And what this image gives us is that dimension, or those Betty numbers. So if you look at the parameter space here is a triangular prism, or triangle across R. And for each point in that space, you can look at the Betty numbers. And my claim is that you can read them off of this picture. So if we look at H0, then the 0th Betty number is at most 2. It's kind of 0 all the way to the left here. It becomes 1 here, and this component kind of extends all the way across. And then there's an additional contribution, which is there is a kind of indecomposable one-dimensional interval module, one-dimensional persistence module here, which gives us another 0th Betty number. So within here, the 0th Betty number is 2. Everywhere else here, it's 1. Over here, it's 0. And so furthermore, all the maps are kind of identity maps, which is something that isn't explicit in this visualization, but is kind of implicit.
But if you took a different affine slice, wouldn't you see a different picture of this wrinkle?
So this is not an affine slice. So unlike, this is not reducing multi-parameter.
Okay, now I understand.
One-parameter persistence.
Yeah.
We are really doing the whole story. Okay, we have a 3-parameter persistence module, and I'm giving you a complete decomposition of that into one-dimensional 3-parameter persistence modules. This is the complete story.
Okay.
Okay. Which is not easy, and we certainly don't have kind of software to do this in general. But we're able to do it by hand, and we're kind of hopeful because, I mean, due to work of like Eli Ashberg and Mishachev, we know that these wrinkles kind of are generic. So I think there is hope of understanding the generic situation, and maybe generically one parameter families of these one parameter families of Morse functions do kind of decompose in a nice way generically using wrinkles, and one can actually kind of explicitly state what the persistence modulos are. I don't know, but it's a dream. And I think if one could certainly prove stuff, the theorems would be very interesting. And then if furthermore you could kind of compute these things in generic situations that show up in applications, that would be fabulous, and would have an impact.
Thank you.
Peter, there's a question in the chat. Would you mind speaking to the open questions left by your curvature and topology paper and the opportunities that geometry brings to the field?
Nice question. Curvature and geometry. This is, if you've read that paper, maybe you could tell me if it's this paper that you were talking about. I know the question's coming from the chat, but maybe that person can. Is this the paper you're talking about? Greg, can you? You said the question came from the chat?
Yeah, it says it was persistent homology detects curvature.
Okay, all right. So this is the paper. This is something I promised to talk about actually in my abstract, but I didn't because I was so excited about the new bio application. I'm actually not sure what the open questions, the questions are referring to.
Sorry, it sounds like there's maybe more possibilities for studying how curvature and like this maybe topological, almost what was considered noise.
Yes, thank you very much. Okay, so this is something that I was excited about a while ago. Maybe when I wrote the abstract, I thought of this, and then I neglected to remember it when I was writing my talks. So in this paper here, we do kind of a baby example of something that I think is kind of a geometric topology, applied geometric topology question, which is if you have a Riemannian manifold with a volume form on it, we can turn that into a probability density if it's compact. So take a closed Riemannian manifold, sample with respect to the volume form. So it's embedded, assume it's same. Actually, maybe we don't even have to assume it's embedded. Sample points, and now assume that we can compute distances between points. Using maybe some local estimates, or maybe just using an ambient metric in Euclidean space. And now, assume we don't know what the manifold is. What can we say about it by looking at those point samples? Now, I think there's lots of approaches to this question using ideas from Riemannian geometry. What if we just use topological data analysis? So can we, for example, estimate the local curvature and assume we're in a setting which is a setting that happens kind of in data science, which is that you can sample points as much as you want. You kind of have a fire hose of points. So pick a local point. You can find lots and lots of points close to it on that Riemannian manifold. Can you estimate the local curvature? So in the paper, we did this. And the bigger question is, can you assemble that local information to tell you more about that Riemannian manifold? So for a while, I had envisioned this kind of research program that would maybe get a bunch of undergrads to kind of do increasingly complicated versions of this where you sample increasingly complicated Riemannian manifolds and come up with TDA invariants that tell you about local structure and patch all that. And think of that as kind of a sheaf on your Riemannian manifold, which for every open set is giving you a persistence diagram and maybe a persistence landscape. So we kind of have an assignment of this Riemannian manifold to a point in a Hilbert space, or an embedding of that Riemannian manifold into Hilbert space. And can we use that to kind of tell us something about the Riemannian manifold? So I may or may not have said something about that at the end of the paper. And I don't know if I'm addressing your question or not, but it's certainly kind of a geometric topological thing that I think is something that somebody could do. So I don't know, did I come close to answering your question, or maybe you can lead me down a different path?
Yeah, it's just like a very interesting idea. I don't know, I found it very interesting. And it seems like you maybe studied like a semi-limited case, and it just seems like there maybe are opportunities to expand it and make it more general. Oh,
certainly, yeah. Yeah, I mean, we looked at just kind of a simple toy example. So yeah, I think there's lots of variations of this that could be interesting. I mean, graph theory is a big subject, and people sample graphs, for example, to extract invariance is one thing one can do. I mean, again, sorry, here we looked at a one parameter family, which was disks of constant curvature. More generally, one could look at configuration space of surfaces, Teichmüller space, sample on that. Maybe one can do, maybe there's an interesting computational topology approach to for understanding these, that says something interesting about these configuration spaces. I guess my caution would be that I think computational topology approaches to these things are likely to be kind of cool and interesting, but probably my intuition is that they're ultimately going to be limited, and that if you really want to prove theorems, maybe the more traditional approaches are kind of the right thing to do, but it remains to be seen.